So in this video, we'll be going over the example of an artillery shell being shot upwards. So we're told that the artillery shell is launched vertically upward from a cannon at ground level. The launch speed is 320 meters per second. How high will the shell go? So we're looking for a height, the maximum height of the shell. The first step in all of our problems is to define our coordinate system, and that's what I've done here. I'm choosing to have the y equals 0 position to be at the height of the cannon, which is ground level. So that means that our height position is 0, which implies that the potential energy at that point is also 0. After we define our coordinate system, now we can draw our diagram. So we have a cannon here. The cannonball is at y equals 0, and it's being shot vertically upward. So we have a V naught equal to, and we're told, 320 meters per second. And then we've dealt with these problems before in Module 2, where the object is now in free fall. So for the motion diagram, as we're going up towards our maximum height, the spacing of the dots is getting closer together. And so once we're at this maximum height, we don't know what this position is. YF is equal to a question mark. We know that the velocity is equal to 0 meters per second. And so this was something that we dealt with in Module 2, where at the maximum height, it's a turnaround point. So the velocity is 0. The entire motion above our 0 point, that's what I'm going to call h. And that's the distance that we're looking for. That's what we're interested in. And at this point, we've defined everything that was given in the problem. So now the next step is to draw a free body diagram for our problem. We've dealt with this before. This is just an object in the air. We're going to be able to ignore air resistance from the problem. So the only force acting on this shell is the force due to gravity. So that's pointing downwards. That's the weight, and that's equal to m times g, whatever the mass of the shell is. We're not given that in this problem. Should also said that the system, we're defining our system to be the shell. So that's our free body diagram. That's taken care of. So looking at it, we only have weight, which is the force of due to gravity, and that we know is a conservative force. So we're not expecting to see any non-conservative forces in this problem. So just filling out the rest of this, we are looking for height, which is going to be a positive number, and that's going to be in units of meters. So now we can plan our solution. We're asked to take an energy approach to this problem. So we start every time for an energy problem, we're going to start with our 7-term energy equation. We've already kind of talked about what some of these terms are going to be, especially the work done by non-conservative forces. Since we don't have any non-conservative forces, that's going to end up being 0, but we'll deal with that down below. The other things that we don't have to deal with springs, so we're not going to define what the spring potential energy is. So all we need to define is what the potential energy can be written as, which is just mg times some height interval. And then the kinetic energy, which is just equal to 1/2 m v squared. So now that we have a plan, we can execute our plan. We've already talked about there's no springs in this problem, so the initial and final spring potential energies are going to be 0 The next step, what we've already kind of talked about, is that we only have conservative forces in this problem. So the work done by non-conservative forces is just 0. Going back up to what's happening physically in our problem and how we define things, we defined our y=0 point, our baseline point, to be where the cannon is launching the shell. So at that starting position, it's going to have a position of y=0. So we know that the height, which is based off of this baseline point, that's just going to be 0. So the potential energy, the initial potential energy, is going to be 0. We're starting off with some velocity at the start, so the kinetic energy, we're actually going to have a value for that at the initial spot, so we're good keeping that there. The potential energy, final, that's going to be a non-zero value because we're going to be at some height above our baseline point. So we'll keep that. And then the kinetic energy final. We know that at the top, it's a turnaround point. So the velocity is 0. If the velocity is 0, that means it has 0 kinetic energy. So that's going to be 0 for the final kinetic energy. So now that we simplified things, we can substitute stuff in. Our kinetic energy is from above 1/2 mv squared. And our potential energy is equal to m times g times h. We have mass on both sides, so those cancel. We're looking for height, so we want to separate h by itself. So we have h is equal to, we divide by g, we get v squared over 2g. And so now we just substitute in. H is equal to v squared, which is 320 meters per second, quantity squared, over 2 times 9.8 meters per second squared. Plugging that into your calculator, you find h is equal to 5.23 times 10 to the third meters, or in terms of kilometers, just 5.2 kilometers. And that matches up with the sign that we were expecting and the units. And the magnitude is what we were given of 5.2 kilometers. So we're good.